Okay. Hello. In today's meeting, we're covering forensics today. So like technically network forensics and hash cracking are part of forensics, but we moved them over to purple team. So this will mainly about files and memory dumps and file system dump, all that. Announcement: Glacier CTF this weekend. Do we have any plans for that or no? Are we just going to attend? How does that work?
It's mostly just gonna be, I think, like playing online.
Okay, yeah. So we'll create a Discord like channel, whatever. We'll just play online. Also, fall break next week. I bet you're all pretty tired. Have a good fall break. So this is a meeting flag, and forensics is usually the gas god category. Because you don't know what tricks they're pulling on their sleeve. Also, the flag is a reference to a thing that I will cover later. Okay, we have this at the end.
I feel sometimes rev jumps everywhere. Sometimes it's at the very end. Sometimes it's like it could be guess cooking.
Yeah. So digital forensics. What is digital forensics? Of course, we're only covering file forensics, OS forensics, which is pretty much incident response, and memory dumps, which is the dump of the entire system. And Sagnik also would like to cover some of the sleuth skit stuff. So there's that. As I said, network, PCAP capture. Those are, I believe, under purple now, as well as some of the hash cracking. So feel free to try them out. We also have purple, meeting recordings that you can refer to. So file forensics. So if you're handed a file, then usually these files all have file extensions, except when it's a binary. And these extensions are merely suggestions of what the file could be. So it's a hint to the users and sometimes the OS, Windows, about the file's intended purpose, but the content can be anything that you want. So in Linux, there's this utility called file. It uses a magic byte or a file signature, or really, the overall structure and all of that to determine the format of the file. So like PNGs always start with those magic bytes that you can see. And if you run, even though this is .txt, it is recognized as a JPEG, which is a different signature than this. It also gives you a bunch of file information that's right there. So does anyone know what is the signature bytes for a PE format? It's actually very simple, 2 characters. Wow. MZ, there we go. So it's actually who the creator of the PE format, Mike Beastkey or something. I don't know. You can look it up. It's a pretty interesting history. So of course we have file, which checks the header of a file, and naturally we would build something that recursively checks all the data in a file, because sometimes you can have data within a file and different files concatenate each other without new files. So that's how binwalk was born. So it finds file formats appended in a file, like file by recursive. For example, some binaries include their assets. So this is the binwalk on cmd.exe. As you can see, it extracts some XML stuff embedded in the CMD. It has like your description, your copyright, encrypted data. I don't know if that actually is encrypted. It might just be some shellcode. PNG image, because sometimes the exe needs to include some assets. Delib compressed data. So you can see a bunch of the stuff are actually encoded and exist within that original file, which you can then use to extract. So binwalk/e will just create, I believe, underscore, like in this case, underscore cmd.exe, this folder. And when you go into the folder, you'll see all the assets extracted. Of course, this is just some sort of matching algorithm. It does not always it's not 100% reliable. Sometimes it will give you some empty files. So just keep in mind. And sometimes it's normal to find other file format in one file, as one file format may use another. The CMD is a good example. PDF is also a very good example. This is my 391 PDF. And as you can see, under the whole PDF document, you have a bunch of zlib compressed data. These, I believe, are images. I'm not exactly sure, but you can see there are a bunch of them because PDFs need to embed image, and there might be plain text, might be a bunch of stuff.
Yeah, I think they are images.
Yeah. And you have this wonderful utility created by, actually, I don't know who created that, but this strings walks through any file and will find plain text strings to the best of its ability. Because, ASCII only is there are only 120 something ASCII characters, and many of them cannot be displayed. So this simply just matches all the valid ASCII character strings that exist in a file, and you can specify how long you want the string to be. Now, of course, if you print n1, that's not very helpful. So by default, it starts with 4, and you can look for something that's greater. So in the same case, you can see CMD. It has a bunch of DLLs that will look for and potentially load. You have the .h file, your header file. You have a bunch of these notifications down there. You have a bunch of Win API stuff, copyright string, as we saw before. So you can actually find a lot of interesting stuff in there.
It is also really funny in CTS because sometimes you could just find the flag by running strings.
Don't spoil it. Come on.
No, I was mainly thinking about goose chase.
Once they hit a hint in there.
That was.
There you go.
I spent a week on that challenge.
So XXD, so this prints a hex dump of file. So, in this format. So you have your line of address, you have your hex characters, and what the translated ASCII is. Now, this is not very helpful in some binary format, so sometimes you still want to run strings on it. And this merely prints the hex dump of a file. So if you want to do anything that's related to editing of the hex file, I would suggest using ghex or hexedit on Linux. And on Windows, I would personally use hxd as my hex manipulation utility. And of course, now Linux gives you this wonderful utility called grep that find a section of the text in a file or a file stream, so you can combine with the previous utilities, like running strings on a file and then grep it, which gives you funny results sometimes, not always, depend on the. Sometimes people have skill issue. Okay, that's what happens. That's what happens.
Better show the actual solve now. You're obligated to go through it.
Yeah, so if you want to see the actual solve, go to UIUCCF public repo, find goose chase or wild goose chase. It's actually a pretty interesting challenge, right? But in this case, unfortunately, he did not do a good job of hiding the flag.
No, it's because I didn't realize this until like the night before, but the sliver decryption key is not recoverable without a memory dump. So I had to throw in a memory dump at the last minute. That's why it came through.
Oh, okay.
Yeah, otherwise I didn't realize it was literally impossible without it. Which, impossible forensics is not something I would live down. I'd rather have this.
You'd rather have grep forensics.
I'd rather have grep than impossible forensics. The only thing worse than impossible forensics is impossible code. There's a lot of impossible code.
Impossible ESO languages.
Okay.
Like the broken hexagony challenge.
Oh yeah, Jesus Christ. Yeah. Okay, so we have steganography. It sucks because it actually does not have any real world use case, but it's just people play with it. So you can use steganography to hide data in other data, which creates inherently guessy challenges during CTS because steganography, you can have a lot of ideas, you can put data in different places, different alignments, whatever, can waste a lot of time. So sometimes you can use statistical approach, and sometimes if you hide shellcode in an image, that it doesn't really work, and you have to be a guess god. So this is image stego, LSB, means least significant bit. Not really used in real world because why would you hide data in an image other than some special purposes, but CTFs love it. The image is mostly unchanged, but you can still extract data because it's encoded at the least significant bit. So in this case, as you can see for this image, you have red, green, blue. You're extracting the least significant bit, and if you have 8 bits, then that's not going to significantly alter the color if you encode data in it, but you can still extract a valid message. Now, of course, it doesn't have to be last bit. It can be last 2 bit, last 3 bit, etc. So as you can see, this gets a little bit guessy. So in this case, you have original and you have encoded. Not much of a difference. But in this case, if you do statistical approach analysis, whatever, you can kind of see. No, actually, this is a visualization of the encoded LSB. So this is all encoded with the same data. And this is a great tool that you can use to look at that. It also has some malicious purposes, interestingly, because in a red team scenario, imagine if you're doing some sort of pen testing to a real world network that's heavily monitored and has some sort of deep packet inspection to see what kind of files you're downloading. Then if you're pulling down, let's say a .py or a binary of some kind, or like some sort of C# code, that's inherently sus, right? Why would a seemingly normal application pull down code from the internet and run it? So in some cases, we can actually encode it, as I said before, and then once the stager receives it, it will decode the shellcode and then execute it. So this is one way to bypass some of the detections right there. So this is a POC. If you guys are interested, you can check it out.
Yeah, this also happened while in Seesaw. One
Yes.
of the challenges did have a bunch of like initial stager shellcode that was hidden inside of it that they had with steg hide, and the goal was to find the malware extracted from that. We got to the stager part. We didn't have enough time to find the actual family, but then it came down to a bunch of other OSINTs. It's also possible for your initial access payload to also be stager. Like I think hunting Blue was one such malware. But yes, this part happens in it.
Yeah, so you can see when you chain stuff together, it gets really messy really quickly, especially with like OSINT and all of that. And oh yeah, so audio stego, you have a spectrogram. Sometimes it will actually write out the message with a spectrogram, and some other times when the message is seemingly random, you have SSTV, which is some sort of like you can transmit TV signals or like images through radio. I don't know how that's possible, but apparently you can do that. And when you have your special files to decode it, and of course when radio signals are recorded, it's an audio, but there are utilities online like QSSTV to decode it. Some sort of frequency modulation. This is this part.
Yes.
If you want, don't actually do that. Most audio stego can be solved with specialized tools. The issue is when you're presented with a seemingly random audio, it's really hard to find these tools. But yeah, sometimes you can, do that.
Yeah. As far as initial analysis tools go, Audacity pretty much covers everything that you need to take like an initial look. You could pretty easily pull up like a spectral analysis on Audacity and then be able to correspond to like your peaks within like your audio image.
You can rule out some obvious stuff.
You could rule out some obvious stuff pretty easily through Audacity, and it's open source. So
Yeah, Audacity is a great tool for audio analysis. So this is kind of like your roadmap. What kind of files is there? What metadata does it have? Like, you can have this will give you a general idea of situational awareness to what kind of challenge you're presented. You can read it afterwards. Also, if it's DOC or DOCM, it might contain macros. And this was not originally there. I feel like if you're presented with some sort of docs file or, some sort of old Microsoft Word or, presentation files, it might embed macros. You might want to check those out. Usually when there are scripts inside of your file, it's pretty important. But yeah, this is the rest of the roadmap. And OS forensics includes log analysis and file system and disk. I'll cover the first part. After that, I'll hand over to Sagnik. So logs can provide valuable information to what happened on the system. If you are given the file system of the OS that you're doing forensics to, of course, logs give you a lot of insight on what happened before. So you have these Linux logs and other various system logs, service log. If they're installed, you can go and check them. You can go and check them out. And if whoever gives this file system has skill issue, you can find bash history and vim info. If you're given these, then it pretty much just shows the entire history of the command they have executed, i.e. what they have done to the system, which can allow you to extract the information pretty trivially. But usually this is just redirected to null, so you don't get anything. And for Windows, you have Event Viewer, include PowerShell script logging. So script block logging is all of your input and I believe output embedded in the Event Viewer, and Event Viewer has some sort of crypto algorithm to ensure you cannot edit it. Of course, there are some, because Microsoft rolls with their own crypto, it kind of sucks, but there are ways to modify the Event Viewer. Overall, it's still pretty reliable. And PS readline module. So this will give you PowerShell output, like the txt file that all the PowerShell commands are executed will be saved in that txt file. So you can go check that out if that file exists and extract what they have ran. And this is the starting point of the OS forensics, and I'll hand this over to Sagnik.
Right, perfect. All right. So normally your entry point will be some form of an archive or zip of the full or partial file system. Get a lot of open space on your computer because it's a whole ass file system. It is pretty large. I know when we look at like the raw disk image files that are given from the zip, it could reach like possibly to like close to 100 gigs if the file system is particularly large. One thing I like to do is put the disk image into like a USB that I can mount. And then when I need to mount the file system, I could keep it through the USB. But normally after you get the disk image, you could run a couple of like stuff for analysis on the disk image because the particularly like the .dd format is all of the raw file system data, and that includes say like where the boot block is. So that's where you are able to find the type of file system that you're mounting. If you're mounting a Windows file system, for instance, there will be bytes that say, hey, this is an NTFS file system. So you're able to find ways to mount that. And detected and deleted files could also be present within the block. For example, if you have like freed up memory spaces, there is a tactic you can do called file carving, which essentially analyzes like the missing bytes in like that file system. And from there you can extract essentially like size info. You can check timelines for like when a file was deleted. Some web browser artifacts could also be saved in like the caches of the file system you're looking for. For example, Mozilla stores them through SQLite 3 files. So you're able to load it in like an SQLite 3 reader and read like browsing history. File systems have a lot of info that you can get from the disk image, and it is a way to essentially do a form of analysis without getting access to like live access to a system. And it is extremely difficult to perform forensics on a live system because you don't necessarily have like evidence could be altered very easily within like a live system. And if you're doing something like say a criminal investigation, it's very difficult to like prove your evidence in court because the image, like, because it's a live file system, one can argue that it might be very difficult to alter the evidence, or not all of the evidence might be able to be trusted on a live system. So if you're on like the criminal investigation sides of forensics, what you'll usually do is you'll take a snapshot of the system and then extract a forensic image as like an exact copy. And you could verify that they're the same by performing, say, a SHA-256 for like a hash, essentially fingerprinting that, hey, I didn't actually change anything in this file system. And then do your operations in read-only mode. But that's something you would do.
You know what I should do? I should make a challenge of file system based on the 391 file system. Like actually,
That
it's
could
not-
be fun.
Yeah, actually, it would not be too difficult, and because I can manually modify my inode, like I can just make the file disappear, and then you have to reconstruct it.
Yeah,
Or like, finding the needle in a haystack and have like 1,000 files, and then you have to reconstruct that one missing file or something.
yeah, these are common problems also found in like file system forensics in the real world. And constructing like a good timeline of things that happen is also like something that could be pretty essential to determine like, hey, what's happened with this file system? So this is kind of like your starting point for that. Going on to a bit of memory forensics. So instead of being given like, say, the traditional file system that you can then mount and put into read-only mode, let's say you were just given the contents of memory or RAM in the form of some sort of like binary dump. Now, dump files are usually created when something like a program crashes or your OS crashes for debugging purposes. And this is in order to take a look at the state to revert back to if something like a kernel panic or something happens. So this means that dump files also contain a snapshot of all of your sensitive info to keep track of like, hey, what happened? Because that'll be sometimes that's really important to have. And it would also find like, say, passwords in your password manager, any kind of like clipboard content that you had at the time of the crash. If you're on Windows, they'll also snapshot the state of like the LSAS registry for those who are in Purple Team. That'll also be present in the dump file. And of course, as you can tell, there's a lot of information and sensitive information that we can extract from this. So.
Hold on, no, okay. Sorry,
Technical difficulties.
technical difficulties.
Oh
You're
yeah,
back.
I just started sleeping yesterday. It's been being like even weirder.
You're back, you're
Oh,
back, you're good, you're good. I was just not thinking when I unplugged that cable, sorry.
Okay. Okay, we're here.
Yeah.
So to analyze memory dump files, there's a tool you can use, a framework called Volatility. And there are two main versions that we have listed over here. Now, Volatility 2.6 is the older one out of the two, but when it's able to work, you can get a lot of info from stuff. Now, this is limited to older OS versions. For example, if something doesn't have like the latest Windows 10 symbols in the dump you're analyzing or the Windows 11 dump, then this might not be as useful because you cannot like take stuff for this. And this used to be a standalone tool. So Volatility will give you like the dump results from that as like a standalone tool. Now, Volatility 3 goes from being a tool to an actual framework that you can use. It's currently still under development, and it is a better OS version to analyze the dumps. And it could be used as a library itself. So you could write scripts that integrate with Volatility 3. So it's a way more powerful tool for analyzing memory dump files. I actually haven't run into a case yet where I had to use volatility. Have you, per se?
Yeah, I have, and there are some I think there are some memory dumps on SIGPwny website that requires you to use volatility. This
Yeah,
can be pretty fun.
Good.
You can go through them. Those are made by like Mason or whoever. I don't remember the name. They're pretty
Maybe
old,
that's
but they're still pretty fun. Go and check them out.
either way, you could set up volatility directly through the source over here. So this will install it as a Python library. And here we have the main framework launcher that you can run on like one of the dumps. So this is the .ps list for a Windows RAM dump. And over here, we can kind of take a look at a table of the different stuff that we have. So, middle one's gone. It's fine.
Yes.
Oh, it's back. All right, so over here, we have a bit of like a couple of fields we can use, like the process ID, whatever file name was currently running, and where in the dump of like the offset in memory that this was there, how many threads were running, and when the process was spawned. So for example, we can look at the dumps here that we can see there could be a service host.exe service that is currently running. This one has a lot of threads currently, and we can see the timeline of the different processes spawning. In the real world, if you're able to get access to a dump from like, say, a soup Greek scenario, where you might be having like, say, malware or injectors that are running under like a process that's been process hollowed, you can sometimes see like when a process that seems anomalous has been created at a time, or when subsequent child processes could have been spawned through like stuff like this. So it is also a very good idea to like look at dump lists in general. So that's one example of the use. Again, a lot of memory can also be stored as string text. Again, string is really good for just extracting any valid ASCII readable symbols. And there's a lot of info you can get. For example, if I want to simply search the dump for any time like text was mentioned, I can simply do the strings and find like wherever there might have been text encoding or some other thing that was running through the dump. And if you're looking for, say, a specific file format, then you can also grab the exact bytes that correspond to the header stuff. So if I wanted to see anytime like, say, a PDF file was opened or something, like I could check the bytes for those, or a PE executable. So that's also very useful. And that corresponds to our section on memory forensics. Next meetings, just enjoy your break. Have fun.
We'll make sure you know at the next meeting.
Yes. So there's the flag, if no one has grabbed it yet.